Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 227, equivalence of expressions in conditionals and biconditionals. Okay, so um, so here's a question. How do we just know if an atom is contained in a subset of an expression? Like, how do we know which atoms are an expression? If I just give you one, how do you know if it is, how it's in there? Well, if that atom merges to true, if that forces this expression to be true, then it must be contained in the subset that this expression represents. Well, to do that, merging the atom to true is like basically what that does. If there's a if this particular atom says that A is true, well, then it'll merge. Then A will merge to true as it merges to true. Okay, so A will go to 1. Okay, in the merge, B will go to false maybe, and whatever else here as we go along. So we kind of can get a sense here for what's happening here as we just replace our variables with what the atom says. Because what the atom says actually has information about what the output of the merge is going to be, and the merge actually preserves these operations. So to get the output of this merge, we can actually replace these with the images, with these guys as images here, and do the operation after the merge on the and after the merge, after everything goes to 0 and 1, we're looking at a simple diagram of 0 and 1. So we're really just doing the operations of and or between zeros and ones on the simple post set. So really we can just do this completely out and see exactly what it is. So this tells me that that this particular atom that I picked is not in this expression if I get a 0. It has to be equal to 1 if it's going to be in that expression. All right. So this is kind of interesting though, because this gives us an important clue how we can create new operations on expressions. If we can create an operation on the simple image post set with just a 0 and 1 on the image, then what we've kind of done is we've generally, kind of given a way of describing it among our expressions. Because the outcome of the operation is the collection of atoms that cause an output of 1. All right, and that's what we want, or true, or something like that, or that actually are working here. And so we can kind of transfer the idea of things happening between 0 and 1 to make a new operation. Here's one. This is notation right here. A arrow B. Let's think about an operation on zeros and ones in the post set of 0 and 1. Let's not look at the Hasse diagram. Let's look at the full picture of arrows in this post set of 0 and 1. Let's, in particular, this is kind of what we're going to think of. For instance, let's suppose that the output of, so let's think about x arrow y as being an expression, which will represent a subset of atoms. Which atoms is it gonna give us? Well, let's think about this for a minute. Let's think about this arrow as okay. All right, so x and y. Okay, so what we're doing is we're letting x and y actually be in 0 and 1. Okay, so this is kind of a way of deciding. So we're kind of working just in 0 and 1 right here. So x is 0 or 1, or y is so Right, so this is going to be an expression between just zeros and ones at the moment, and we're going to let this expression output 1 or true. So it's only going to go to here or here, right? It's going to either be this one or this one. So this expression is either the 1 or the 0 expression in this 0, 1 world right here. And it's 1 if what? If x is a subset of y. Or there's an arrow. And it's 0 if not. All right. So basically, if this arrow represents one of these arrows, that's pretty much what we're saying. So notice that 1 to 1 works, 0 to 1 works, 0 to 0 works, but 1 to 0 does not work. That's the only one that doesn't work. In fact, you'll see that right here. 1 to 0 doesn't work. So, so that's kind of after a merge of everything, I guess. But let's kind of look at expressions that aren't just 0 and 1, like, A arrow B. A arrow B will become an expression. Now, how do we know which atoms to include in the subset that describes it? Well, each and every atom creates a merge to 0, 1 when we merge it to true. And in that merge, we have to ask, has the expression, in that merge, A will go either to 0 and 1, and B will go to 0 and 1. Then we'll have a new expression between 0 and 1. And if that expression ends up being the 1 expression, then we know to include that atom that made that merge. If it's the 0 expression, don't include that atom. So we've actually made a new operation because it definitely outputs. It's a well-defined output for another expression, which we could say is a proposition in our logic. So it works. It's an operation. All right. And how can we? Okay, so for instance, is TT in this expression? Well, we can check it out. TT, well, to apply the merge, we put 1 to A and 1 to B, and notice, yes, there's an arrow in 1 to 1, so it is. So A to B includes TT. It actually includes FT as well, because there's an arrow that goes from 0 to 1, and there's an arrow that goes from 0 to 0. So these are the ones that includes. The 3 arrows represent the 3 things that are included in the atoms, TT, FT, and FF. It's basically like saying, if A, then B. If A is true, then B is true. But if the hypothesis, if A is true, is not satisfied, then we still think of the statement as valid and true. It's kind of like a conditional. So this is called a conditional statement. If A, then B, but we allow it to be true if the hypothesis is not valid. So this is called a conditional. If A, then B. And in particular, see how this atom right here can actually be written like this, and its complement is actually this. So we could actually write it. Another simple way of writing down this operation, if A, then B, as a conditional, is just simply not the expression of A and not B. And we can use duality, De Morgan's law, distribute this not across, and then what happens? This and changes to an or, and that not B is just B, so not A or B. This is probably the simplest way of writing down if A, then B. That's another way of writing. So if you ever see something like this, you can rewrite it in terms of ors, but that's kind of what it means. Okay, so, all right. Conditional implication. So the statement is the proposition P arrow Q is true. But that proposition could be either true or false. So it's kind of a statement about, so this is another way of saying what it is. It's a statement about P being a subset of Q. And I guess subset of Q could potentially mean that P is the empty set. So, I guess that's where that comes into play as well, or at least merges to that. So, that's really all it is. It's a subset idea. But it's not just a subset idea. It's like a statement of it is true, right? It is true that this is a subset of this. And well, that statement could be either true or false. Whereas if you actually write down P subset of Q, we haven't said that that's true or false. We just said it flat out. And we won't be able to say it if it's not true. So it's a much stronger to say P implies Q than it is just to say P to Q, because this is still a question. Is this true? We don't know. Okay. So, all right. And there's various notions that we can work with. I want you to caution you right here. If you negate the arrow, it doesn't change any direction with arrow. In fact, it's not even, it doesn't work the same way as, so this arrow and the negation doesn't really work because of what the statement is. It's a statement about whether something, the statement of being a subset is true or false, but it's not actually, this is actually not the subset arrow, and it doesn't behave the same way with the negation symbol. So we cannot use the negation in that particular way. So then, okay, all right. But we do have a few things that are true, like this. P, but these two things are the same, though. They're actually equal, all right? So P arrow Q is the same thing as not Q arrow not P. Keep in mind that P arrow Q is actually one expression. It's actually one statement. It's like, we're not putting subset things in. This is just an actual expression. So this is like an operation, just like and or is, okay? And these are the same things because complement, subset of complement this way is equivalent to the other ones. The question whether this is true is the same as the question whether that's true. So those are the same thing. I mean, if two expressions contain the same atoms, then they're logically equivalent. Okay, and if you have, all right. Okay, and what does this mean? This just simply means, okay, logical equivalence, that just means that they're subsets of each other. They contain the exact same atoms. And so those contain the exact same atoms. So there's just different ways of thinking about this. What does this expression mean? This is a biconditional. This just is the and of these two expressions. Q, and if Q then P, or P if P then Q. It's just the same thing. And actually, we can picture this idea on the poset 0, 1, like we were considering arrows, but we're going to consider arrows that are both ways that go. So basically, the reflexive arrows, the arrows that are self loops, it's only two self loops, 0, 0 and 1, 1, and the other ones, this is an arrow. That doesn't work. That's not there's only an arrow one way. It's not a self loop. It's not a loop. So 0, 0, because this means it goes both ways. So you could think of it the same way and kind of construct that idea that way. And so you can actually write this down if you want as C. Both P and Q have to be 1, or they both have to be false in order for it to work. So this is another way of writing it. So if you ever see P biconditional Q, another way of writing it is this way right here. And then here, if you reverse this conditional arrow, this expression is called the converse of the other one. Okay. And then there's some examples here at the end of the section. Okay, we can take this expression, convert it to disjunctive normal form by simply thinking about what the atoms are. And you take the atoms and you union them up like this. So you write them as expressions, the atoms as expressions, and you union them. That's disjunctive normal form. You could do sandwich swallowing or whatever else if you wanted to, but you would end up getting a not A or B as desired. You can kind of look through that. Here's another one. Let's write this in simplified conjunctive and disjunctive normal form. So to do that, first of all, let's think of it this way. We have something goes to C, or conditional C. And this, there's a way of rewriting this in terms of ors. And if you remember, it's not the first thing, or the last thing. Okay, then we just have to look at what goes in here, the something. All right, in that's right. Okay, in disjunctive null form by thinking of its atoms. Okay, its atoms are this, and we write it as an or, and notice we replace it where the something was. We distribute the not through, and it becomes an and here, right? And then we can distribute that distributive property. We get disjunctive normal form. Okay, and no swallowing. It's a simplified form, and then we can FOIL it out the other way to get disjunctive normal form simplified. So basically, the crux of these are some examples of what we can do with expressions that are built with these arrows, and how we can simplify them into as simple as we can. But logically, what do these arrows mean? They basically mean just statements of implication as expressions, as like, I don't know if this implication is true or false. So really, we use them all the time when in proving things or stating if this happens, then that happens. But we just like, so basically it's a statement. If A happens, then B happens. That's all it is. It's just that statement, but we're not, but we're letting it be a logical statement. When we let it be a logical statement, then it becomes these arrows, not the double ones, but just the single ones. They either go that way or, well, I mean, I guess you could call it double, but I mean, what I mean is like a line here and a line below it. It's just a single line going with an arrow on this side, or and or an arrow on that side for a conditional or a biconditional. Lastly, the last thing here, you can make a truth-false table, where if you have like 3 expressions, you can write out, these are basically different atoms, and the atoms that work in the expression are the ones that make up the expression itself. So in Sage Math, you can actually do this. In fact, you can right-click right here, and if you do so, it'll take you to Sage Math and put all this code in, and you can run it, and you'll actually, this code is actually put in for you when you click this, and so it runs itself, and you can see the output. You can modify it from there, so here's an example of an expression that you can put in, and then it tells you information about that expression. In fact, this expression is represented by those. If you use a table like this, it's really nice. It's really easy to get something in disjunctive normal form, because disjunctive normal form is actually, you just take these 3, see these 3 atoms right here? These are the ones included. So you basically have like A and not B and C, and that's one thing. Put parentheses around that, then you OR it to A and B and not C. So that's one thing. And then you OR it to A and B and C. And actually, that's disjunctive normal form right there. You could sandwich ball in that and simplify it down. So putting things in a table like this is kind of nice to use technology sometimes. You could make your own table yourself just by plugging things in, as we were doing before, and seeing how it works. In fact, I give you a description of how to do that right here. Okay, and maybe just at the end, I'll just control click this to show you what happens. So I'll open, let's see, I'll open link in a new tab, and see, I'll come over here. And then when I open up the link in this new tab, come over here, and so this is what happens here. The Sage code is right here, and it's evaluated here. That's how I get my table, and then I could change this expression if I wanted to something else, and I can also see a similar table. For instance, let's just do a simple one like A arrow B and evaluate, and see I get my table right here. of different things that have different values. Um, or I could do let's just show you different. So A and B, I could do right here. So that's the symbol I use for and. Or I could use A or B. So this is kind of the long vertical line on the keyboard here, A or B, and that tells you here. So A or B is only false when both of them are false. So see, there's different things, expressions you can build here, and this is kind of a nice feature of Sage Math, and it's built right in here. There's from the book you can click, and this gives you a way of working through this here. Okay, thank you for watching.